Hi, in this video, I will be teaching you how to perform test of significant difference for 3 or more independent groups in RStudio. When we do such test, it is important to know which of the 3 tests, one-way analysis of variance, one-way analysis of variance with Welch Correction, and Kruskal-Wallis Test should be used to analyze the data. Test concerning means or medians for more than 2 samples. Compare the means or median of 3 or more independent groups in order to determine whether there is statistical evidence that the associated population means or medians are significantly different. These are useful in the following situation. Suppose you want to test the effect of 5 different exercises. For this, we recruit 20 men, form 5 groups out of them, and assign one type of exercise per group. Their weights are recorded after a few weeks. And you want to study the effect of fertilizers on yield of wheat. We apply 5 fertilizers, each of different quality, on 5 plots of land. The yield from each plot of land is recorded and the difference in yield among the plots is observed. Notice that in these examples, we have 3 or more independent groups to compare. Let's discuss the one-way analysis of variance, also known as one-way ANOVA. This test is used to determine whether there are any statistical difference between the means of 3 or more independent groups. The R function for this test is given below. AOV function allows us to perform analysis of variance in RStudio. Dependent contains the variable that was measured during the data gathering procedure, also known as the dependent variable. Group contains the grouping variable, also known as the independent variable, whereas data is the object that contains the variables. The assumptions of the test are the following. Your dependent variable should be measured at the interval or ratio level. The data are independent, which means that there is no relationship between observations. There should be no significant outliers. The variance of each group should be equal. And your dependent variable should be approximately normally distributed. The first 2 assumptions can be easily controlled when you plan your research instrument and your data gathering procedure respectively. However, for the third assumption, boxplot can be used to identify possible outliers in the dataset. For the fourth assumption, for as long as the sample size of each group is equal, this is not an issue. If you want to read more about this, the link to the paper is given below. However, if it is not, we will be using a corrected version of the test which will be presented later. Finally, for the fifth assumption, we will be using the recommendation presented by Zimmerman in his article, A Simple and Effective Decision Rule for Choosing a Significant Test to Protect Against Non-Normality. To read more about the article, the link is in the description below. The decision rule will be discussed later. If the sample size is not equal, it is safe to use the one-way analysis of variance with Welch Correction. This test, also known as Welch ANOVA, compares 3 or more means to see if they are equal. It is an alternative to the classic ANOVA and can be used even if your data violates the assumption of equal variances. The R function for this test is given below. One-way.test function allows us to perform analysis of variance in RStudio. Dependent contains the variable that was measured during the data gathering procedure, also known as the dependent variable. Group contains the grouping variable, also known as the independent variable, whereas data is the object that contains the variable. The assumptions of the test are the following. Your dependent variable should be measured at the interval or ratio level. The data are independent, which means that there is no relationship between observations. There should be no significant outliers. And your dependent variable should be approximately normally distributed. Basically, the only difference in the assumption of Welch ANOVA to classic ANOVA is that the former does not assume that the variances among groups are equal. If the data violates any of the assumptions, we use the Kruskal-Wallis test. This test, also known as one-way ANOVA on ranks, is a rank-based non-parametric test that can be used to determine if there are statistically significant differences between two or more groups of an independent variable on a continuous or ordinal dependent variable. The R function is given below. Kruskal.test function allows us to perform a Kruskal-Wallis test in RStudio. Dependent contains the variable that was measured during data gathering procedure, also known as the dependent variable. Group contains the grouping variable, also known as the independent variable, whereas data is the object that contains the variables. The following flowchart will help you decide which of the three tests will you use for a 3 or more independent sample test of significance. We first ask if there is at least one outlier in each group. We may use the box plot for this task. If there is an outlier, we use Kruskal-Wallis test. Otherwise, we check if the variable is normally distributed when grouped according to the independent variable, using the decision rule suggested by Zimmerman. I made a script to make this process easier. All you need to do is download the script in the description below. If the script suggests using ANOVA, check the number of observations per group. If they are equal, then use the classical ANOVA. Otherwise, use Welch ANOVA. Now, let's perform a test of significance for 3 or more independent groups. In this demonstration, we will be using the performance dataset available in RStudio. To view the data, type library, open parentheses, Deuterium. Enter, view, open parentheses, performance. Highlight the code and press Ctrl Enter. If you were not able to install the Deuterium package, you must first install it. To install the Deuterium package, type install.packages, open parentheses, quotation mark, Deuterium. Highlight the code and press Ctrl Enter, then highlight these codes to view the dataset. The dataset contains 60 observations with 5 variables. For this demonstration, we will be using the stress and T1 variables. Suppose you want to test if there is a significant difference in the performance of employees on the first month when exposed to different levels of stress, low, moderate, and high, at 0.05 significance level. Now, we will select the test that we will use for this dataset. First, we must check if there exists one outlier in our dataset when grouped according to the stress variable. We type boxplot, open parentheses, T1, tilde sign, stress, comma, performance. Highlight the code and press Ctrl Enter. In the plots window, we see the result. It appears there is no outliers in each group. Next, we use the script that checks if the data is normally distributed when grouped according to stress variable. But before that, download the script using the link provided in the description below. Once you're done downloading the script, open it by clicking File, Open File, and locate the file. In my case, it is here. The file name is Normality2. Double-click the file and you will see the script. Just a reminder, do not edit the script. Highlight the entire script by pressing Ctrl-A and press Ctrl-Enter. Go back to the previous window and type Normality 2 open parentheses, performance, $T1, comma, performance, $stress, comma, performance. The normality2 function allows us to check if the assumption of normality is satisfied based on the recommendations of Zimmerman in his article when using test of significant difference for 3 or more groups. Performance $T1 is our dependent variable. Performance $stress is our independent or grouping variable. And performance is where these variables are stored. Highlight the code and press Ctrl-Enter. The script will run the necessary analysis, and all you need to do is to follow the decision presented in the output. If you want to know more about the decision rule, I highly suggest that you read the article, which can be accessed on the description below. The result suggests using ANOVA for this dataset. Now, we check if the sample of each group is equal. We type library, open parentheses, declare. Enter. Performance, percent greater than percent sign. Enter. Group underscore by, open parentheses, stress, forward percent greater than percent sign. Enter declare, double colon, summarize, open parentheses, count equals length, open parentheses, T1. This line loads the declare package. Performance contains the dataset that we want to analyze. Group underscore by stress argument indicates that we will group the dataset according to stress variable, whereas this argument indicates that we want to count how many observations are there for each group. Highlight the code and press Ctrl-Enter. We can see that there are equal number of observations in the two groups, which is 20. Therefore, we will use the classic ANOVA. The next step is to formulate the null and alternative hypotheses. The null hypothesis is there is no significant difference in the mean performance of the employee when grouped according to stress level, whereas the alternative hypothesis is that at least one group is significantly different from the other on average. It is noteworthy that for these tests, the classic ANOVA, Welch ANOVA, and Kruskal-Wallis Test, it cannot identify which among the group is significantly different from the others if we accept the alternative hypothesis. These tests can only suggest at least one group is significantly different from the other. If we want to know which group is that, we need to use post hoc tests, which will be discussed in the next video. Now, let's perform a classic ANOVA in RStudio by typing result, AOV, open parentheses, T1, tilde, stress, comma, performance. Enter. Summary, open parentheses, result. Result object is where we will store the result of the one-way ANOVA. AOV function allows us to perform an analysis of variance in RStudio. T1 tilde stress argument indicates that we need to group the T1 variable using the stress variable. Performance argument indicates where these data are stored, whereas the summary result function allows us to see the ANOVA table that we need for the interpretation of the result. Highlight the code and press Ctrl-Enter. In the console window, you will see the result. This row is the between treatments row, whereas the next row is the error or residuals row. Therefore, 2 is the degrees of freedom between treatments, 57 is the degrees of freedom of the errors, 0.8235 is the sum of squares between treatment groups, 1.6190 is the sum of squares error, 0.4117 is the mean square of treatment, 0.0284 is the mean square error, 14.5 is the test statistic, also known as the F statistic, and 8.13e negative 06 is the p-value of the test. 8.13e negative 06 is equivalent to 8.13 times 10 to the negative 6 power, which is a very small number. Hence, we decide that there is sufficient evidence to say that at least one group is significantly different from the other at 0.05 significance level. Since we found out that there is sufficient evidence to accept the alternative hypothesis, a post hoc analysis is needed to further analyze the data. However, we will discuss that one on the next video. For the next demonstration, we will be using the business dataset, which can be downloaded on the description below. Once you're done downloading the file, we type data1, read.csv, open parentheses, file.choose, comma, header equals true. Highlight the code and press Ctrl Enter. Look for the file and double-click it. In the environment or history window, you can see the dataset. For this demonstration, we will use the age and opportunity.evaluation variables. Suppose you want to test if there is significant difference in the opportunity evaluation score when grouped according to age at 0.05 significance level. Now, we will select the test that we will use for this dataset. First, we must check if there exists at least one outlier in our dataset when grouped according to age. We can do that by typing boxplot, open parentheses, opportunity dot evaluation tilde age, comma, data1. Highlight the code and press Ctrl Enter. In the plots window, we see the result. It appears that there are no outliers in the dataset. Now, we use the script that checks if the data is normally distributed when grouped according to sex. Since we ran the script earlier, we may proceed typing the function normality2, open parentheses, data1, $, opportunity evaluation, comma, data1, $, age, comma, data1. Highlight the code and press Ctrl Enter. Based on the result, we have to use ANOVA. We will check if the sample of each group is equal. We can do that by typing data1 % greater than %, enter, group underscore by, open parentheses, age, forward % greater %, enter depleer, summarize, open parentheses, count equals length, open parentheses, opportunity dot evaluation. Data1 contains the dataset that we want to analyze. Group underscore by age argument indicates that we will group the dataset according to age variable, whereas this argument indicates that we want to count how many observations are there for each group. Highlight the code and press Ctrl Enter. We can see that the number of observations in the two groups is not equal. There are quite a number of observations under above 40, whereas fewer observations on the other age group. Hence, we will use the Welch ANOVA. The next step is to formulate the null and alternative hypothesis. The null hypothesis is there is no significant difference in the opportunity evaluation score of the respondents when grouped according to age, whereas the alternative hypothesis is at least one group is significantly different from the others on average. Let's perform a Welch ANOVA by typing oneway.test, open parentheses, opportunity evaluation, tilde, age, comma, data1. Oneway.test function allows us to perform a Welch ANOVA in RStudio. Opportunity.evaluation tilde age argument indicates that we need to group the opportunity evaluation variable using the age variable, whereas data1 argument indicates where these data are stored. Highlight the code and press Ctrl Enter. In the console window, you will see the result. The F, which is equal to 3.4988, is the test statistic. NumDF, which is equal to 4, is the degrees of freedom in the model. DenumDF, which is equal to 12.938, is the degrees of freedom associated with the error term, whereas the p-value, which is equal to 0.038, is the probability that you will get your data assuming that the null hypothesis is true. Since the p-value is less than the significance level, which was set to 0.05, we reject the null hypothesis and accept the alternative hypothesis. Hence, at least one group is significantly different from the others. Like the previous example, we need to perform a post hoc analysis to identify which among the group is significantly different from the other. We will discuss this in the next video. That ends the part 1 of the video, Test of Significant Difference for 3 or more independent groups. In the next part, I will demonstrate how to perform Kruskal-Wallis Test in RStudio. Thank you very much and have a great day.